so maybe if you want, you can say a few words about yourself so everybody knows everybody. I will just start. It would be great if you could say maybe your name, where you're from, and also maybe your what you do, like which job, but also how much you have used the toolbox before, right? So we get an image whether you're completely new with it or whether you've used it a lot. Right? So I'm Andy. I'm from Berlin, Germany. I work as a neurologist or in training. And I also developed this toolbox, and I'm really happy that you invited me here to give this workshop. Maybe you can go next.
Hello everybody, my name is Wang Di. I come from Beijing. I'm a student in Connectomics University. I study in clinical medicine. And I use this toolbox to reconstruct the epilepsy patient's electrodes. It's really a very good software, and I like the feature very much. Hi everyone, my name is Vera. I come from Connectomics University. I'm a student now. My major is neurology. I don't know how to use this software, but I would like to learn.
My name is Toolbox.
Hello everyone, my name is Gao Huan. I'm from Fudan University. My major is mechanical engineering. So I haven't used this software, so it's my time to learn.
Hello everyone, my name is Anjawi. I'm from Fudan University and I'm a major in neurosurgery. Nice to meet you all.
Hello everyone, my name is Zhang Bo. I'm from China Academy of Science from Shenzhen. And my major is managing single unit recording in Monday. And I have now experience with Lead DBS. I have a friend to analyze some patients' data, so I wanted to learn DBS in this time.
I'm Li Nan. I came from Xi'an Hangzhou Hospital. I'm a neurosurgeon and a very first user to this toolbox.
Sorry, I just a little bit nervous. I'm Yang from Tsinghua University, and I'm a neurosurgeon. I come from Beijing Tsinghua Changning Hospital, and I have tried this software before and several times. And because with my colleague, I've done different stimulation, and I tried software, but I got some questions with it. And this time, I really want to register the MER data to the lead position. And in the first introduction from Hong, and I saw that you would like to teach us. But in this newest program, I don't see this how to register the MER data, obviously.
Okay, we'll do that.
My name is Juju. I'm from the functional neurosurgery department of Fudan Hospital. I'm a neurosurgeon. And I never used this software before, so I can't know how to use it.
Hi, hello everyone. Good morning. My name is Zhang Yiqing from Beijing Hospital. I'm never use this.
Hello everyone, my name is Sushida. I'm from the National Engine Electrode or Neuromodulation. I have used it from last year. I'm concerned about how can the software can use it to be for clinical use. Thank you.
My name is Dan Hong. I'm from Shanghai Mental Health Center. Just would like to learn some DBS in psychiatry disorder.
Hi everybody, my name is Hu Yu. I'm from Brenna. that comes me to learn the DBS. I tried that many times before. So I want to have a deeper understanding of their toolbox.
Good morning, everyone. My name is Gong Wei. My name is Kate. I come from West China Hospital. My major is neurosurgery and work around.
Hello everyone, Wei Rong. I come from West China Hospital. This is my first time to study how to do this Toolbox. So thank you very much.
Hello everyone, I'm Fudan University and I'm from the University of Chinese Academy of Sciences and Institute of Psychology. But actually, I will move to the Institute of Neuroscience next month. And I come here to the DBS for the first time. And in the future, we will take part in some technology study of the cognitive impairment of Parkinson's disease. So it will be glad if we can collaborate in the future. Yes,
Good morning, everyone. My name is Tang Lu. I come from Shenzhen Second People Hospital. I'm a surgeon focused on the University for movement disorder. I have said hello to Andy on the week Peter. I'm the colleague of Yao Chen. You have known him. Yeah. I came with the brief research in Hive with me to the workshop. Thank you much.
I'd like to, yeah.
And now in our hospital, we have performed around 180 DBS surgery, and we have used this toolbox to assess the electrode placement after the surgery. And now we plan to investigate the function connectivity by working with MRI before and after the DBS.
My name is Fudan. I come from Beijing Hospital. Beijing's cadaver of neurophysician and the Beijing Laboratory of neurophysician. I want to use this for the reconstruction because but actually global physics, internals and subatomic nuclear field one special. I want to use it to analyze all electrode data.
Good morning, everyone. I'm also come from Beijing Shanghai Hospital and co-workers with actually for the DBS, schools and the cleaners and this.
Hi everyone, I'm Ian. I'm coming from Tremor University and I've been quite friendly with half there in this room and quite thankful for Andy and Julie for and also recently I moved to learn about and how to reconstruct so
And maybe you as well?
Hello, I'm Jie from Beijing Hospital, and I'm here in neurosurgery.
Hello everyone, my name is He. I'm from Fudan Hospital, Fudan University. I'm a neuroscience student. I major in Parkinson's disease and take links into simulation. I have used the software several days ago, but I have come across some programs. So I'm very glad to have a chance to learn here. Thank you.
I'm Zhao Na. I'm from Hangzhou University, and I'm majoring in neuroscience. So I try to find out information about DBS. Okay.
I'm Hong Zijie, also from the Connectomics University. I saw a paper on law that said the DBS, so we are majoring in GMS, so we want to learn some information about this.
Hi everyone, my name is Jing, and I come from Hangzhou University.
Hello everyone, my name is Nifei, and I'm currently working in Shanghai University, and I also come from Berlin, Germany, and I work with Andy on this DBS project for years. And I'm a computer scientist, and my major interest is neuroimage analysis.
Hi everyone, I'm Simi from Fudan University, and thank you all to come here to join us to learn this fantastic toolbox. If you have anything to ask us for help, we'll be very pleased to help you here. Thank you.
Sorry. I'm Juan Lorenzo. I'm working at the University of Lead Valley. I'm from Argentina, Mercedes from South America, from Peru. And we are doing evaluation research. It's our main
So you have been using it?
Yes. Juan Lorenzo.
And the last, I'm Federica. I'm also working in Andreas. I'm going to give two talks today and one tomorrow. And I'm a PhD student in my last year at the University of Berlin. And I'm working with brain stimulation in a more cognitive neuroscience setting, but working with Parkinson's disease patients and also looking at different disease patterns and how they maybe translate from the clinical or from the research context into the clinic.
Okay, so once again, thank you so much everybody for your interest, and Xini for organizing. Thank you so much, and Shuyan Wang. And we're really happy to be here. China is such a beautiful country, and we plan this to have a few theory sessions, but also a lot of hands-on, so where you then really use the toolbox. In these sessions, if there are problems, we thought that everybody who's not giving a talk, currently Lingfei, Friederike, and maybe also Xini, can help you as well, assist directly at the computer. Did everyone get this installation? If not, it's not so important now, but if not, you can also ask Lingfei for help to get the newest version. And I'll start with an introductory talk about the workshop and about Lead DBS. So this is what this is about, right, in a nutshell. So we are interested in finding out where the electrodes are from DBS patients, and that these can be implanted everywhere in the brain, basically. These are fornix data from Lausanne, so from Toronto. So it doesn't need to be a subthalamic nucleus electrode. And we want to know where exactly in the brain it is. We also want to maybe be able to stimulate one of the contacts and get an idea of the amount of brain tissue that is being stimulated. And then we can also use tractography to maybe get some inferences about what brain areas might be modulated by DBS. And this is the outline. I think everybody has that. So we are more or less trying to go through the toolbox, through each step, and also have a few other talks. Like tomorrow, there will also be two people from Luxembourg, so Frank Hertel and Andreas Husch. We will probably switch the program because they want to have one talk only together. So we will have to move those. And then Friederike is going to talk about her research as well, and Lingfei. And yeah, that will be the program. And very important, really, please interrupt us at any time if you have questions. So we want this to be interactive and friendly. You can ask everything, and we really want you to take home as much as you can, right? So don't be shy, please interact with us. And we don't have to stick to the program exactly, right? If there's one topic that you think we need more time, we will just take more time. Or if we can be quicker, we can be quicker, right? So we are really flexible, and please interrupt. One other maybe important thing is that we currently just have a new paper out about the newest Lead DBS version, which I think is a good overview for, a scientific overview, because there we really try to write up the newest methods and the newest pipelines and so on. That's why if you don't have it, it might be good to download it, because there's also this figure in the paper, which basically shows a guideline through all the standard steps, right? So we usually start importing images from the scanner, and then we do co-registration and so on, then we go to do normalization and so on. And as you can see, for example, for normalization, we have a lot of options in Lead DBS, so you can choose, but this can also be, in the beginning, it can be a bit weird, so that you have to choose so many things, so we have a default selection there, right? So this is a central figure for this, and this is the DBS pipeline. We also then have the Connectome pipeline, and there's also basically a default pathway going through. This is also maybe a more general idea that Lead DBS is a really open science or open source toolbox. It's meant for research, it's actually not meant for clinical use. I think there was one question, but it's more intended to do clinical research. And the nice thing about it is that we can use a lot of other open source toolbox, right? So this is just an overview of with how many different softwares you can interact with Lead DBS and plug it in and put your analysis into a larger framework. For example, this software Pacer here, that's the one that Andreas Husch develops, who will come tomorrow, and we could integrate it into our tool because everything is open source and everything is basically free. Okay, so brief outline of this current talk. I'll give you a few slides about motivation. Why do we want to know where the electrode is? For most people that's obvious, but still I have some slides. Then I'll also show you a few available software tools, because Lead DBS is not the only tool that can do this. And then I'll also show you some applications of how we use Lead DBS clinically, just to get an idea. Okay, so motivation. We want to know where the electrode is. DBS electrode localization. And okay, so DBS electrode localizations, we might be interested in just to know which anatomy part, in which part the electrode is. Then we have, in Berlin, we've done a lot of studies about electrophysiology, so we basically recorded from the electrodes with local field potentials. And then we wanted to know from where did we even record. Just wanted to get my pointer quickly. Sorry about that. Yeah. Okay. So anatomy, electrophysiology. Sometimes it's about clinical evaluation, right? We want to know which part of the subthalamic nucleus maybe gets the best clinical result. And the method itself is interesting, we think, because it's challenging for imaging. So we really want to know precisely where the electrode is, and people also like you, maybe Tinya, find it interesting to know where the electrode is and to improve this. And then it could also be a quality management process, right? The surgeon puts the electrode in, you localize it, and he or she gets feedback where it is and maybe improve. Other motivations, so why do side effects occur? Why do we have side effects in some patients? Why do we have patients that don't respond? And currently the other thing is that once we put the electrode inside the brain, the neurologist puts in a programming and says maybe take the lowest contact, and it's a trial and error approach, right? He tries and tests clinics and tries the other things. So we want to improve this to be able to see which one is the best contact. So scientific reasons then, there's this technique or method that you can use with Lead DBS, which is to localize electrophysiological signatures to the brain, and we have published a few papers on this, also other groups have started. Then some people are more interested in connectivity from the electrode and what connectivity profile is maybe best for patients. And then there are also some studies that try to combine electrophysiological signatures with connectivity profiles. And then, of course, some people started to use, to try to find out where the electrode needs to be to have a good clinical outcome, where you have more side effects and so on. And then some studies just use it to make sure it's in the right place, right? So they maybe record from the subthalamic nucleus, they want to know it's really inside the subthalamic nucleus. Okay, now I talked briefly about challenges in DBS imaging. So I call this DBS imaging, so it's imaging, MRI imaging in the DBS world. And one challenge is really the resolution. So here you have 3 electrodes from 3 patients. That's the subthalamic nucleus, so it's a Parkinson's cohort. And these are the active contacts, right? So the red ones are the ones where the neurologist put on voltage. And you can see that the distance between these 2 active contacts is roughly 2 millimeters. It's not far, it's really close by. But this patient is really close to the sweet spot that had been published 2013. And if you're further away, you have less improvement, right? So you can see now that number 51 had a roughly 20 or 25% improvement, but this patient had a 80% improvement. So it's a big difference in the clinical improvement, even though it's only about 2 millimeters distance, right? And the challenge in imaging is now to resolve these small distances, right? We want to see this, and it's not easy because most of the methodology we are using to do this has been developed for functional MRI, right? Because that's the imaging world, so the normalization, SPM, and all these tools have been used for functional MRI, and here 2 millimeters are not much difference. Right? So people ignore 2 millimeters in fMRI, whereas in DBS imaging we really need to focus on the very small distances. Okay. So you always have to bear that in mind, that reconstructing an electrode needs time and attention. So it is, millimeters matter a lot, and your analysis will get good results only if you are really careful and really know what you're doing. If not, it will not work. The other problem is that we are dealing with structures in the brain that are very complex. They're very small and complex, right? So this is the internal pallidum, the TPI, where we put electrodes for Parkinson's, but also dystonia sometimes. And if you're on a normal MRI image, you're lucky to be able to identify the TPI from the TPE, which is this structure here. And usually you don't see this lamina, so the division between the two too well. But here on this is a post-mortem 9.4 Tesla image that was scanned the whole weekend, so it's a really great MRI. You can even see the lamina that divides the TPI into 2 parts, right? So the structure itself is very complex, and usually we don't see that on the MRI. So maybe a brief interim summary, what will this course deal with? It's going to be about connectomics as well, a bit, DBS electrodes, network simulation, but also you should focus a bit on neuroanatomy, right? So you should be interested in trying to find out the small details in neuroanatomy. Okay, so what available software, what is out there on the market to do this? Of course we have Lead DBS, that's why you're here, and we will focus on this tool, but I find it only fair to also show what other options there are, right? So I think one other good option to use is called DBS Proc, and this table is also in our paper, so if you want to look it up. DBS Proc is also open source, it's made by the NIH and Bethesda, it's publicly available, open source, free of cost. It's not approved for clinical use, Lead DBS is not approved either, and it basically builds on the AFNI pipeline. If you know neuroimaging, it's a bit like SPM, but AFNI. Then there's PyDBS that's unfortunately not really available, but it is being developed by the French group, so by Den and Paris. And I think if you're interested in using it, you could also contact the authors. Pacer is now part of Lead DBS, but also works and is really cool as a standalone application. So if you're really good with imaging, you just need a very small tool. Pacer is really cool. So Andreas Husch will be here tomorrow and we'll talk more about it as well. Then there are some more softwares that have been published but are not really available. But there are people at least that try to or develop something similar. Cicerone DBS used to be the first that I know of, first software by Cameron McIntyre's group, but it's discontinued. It has become the guide software here. And Guide itself is also discontinued, but now they have Guide XT, so these are the commercial applications here. BrainLab, we have one person from BrainLab in here. They developed this, and as far as I know, it's already available. At least I know labs that use it in Germany. Then there used to be Optimize by Medtronic, which came out of the Cranial Cloud, Cranial Drive tools by Pierre Dehaze. It is also discontinued. Then SureTune is also discontinued in the original form, but Medtronic has now a new version of SureTune, which I think also is available. And then what's definitely available is Cranial Cloud and Cranial Drive by Neurotargeting LLC, which is also like commercial software to do this. And I think to differentiate between scientific use and commercial use is really important, because there's probably not one tool that can serve all of the purposes really perfectly. So, for example, Lead DBS is not approved for clinical use, right? It's not officially allowed to use it for clinical use, whereas the commercial applications usually file for CE mark or for FDA approval and so on. And maybe a downside in the commercial applications is that they are not open and you cannot really access the data so easily. So if you want to do research, it sometimes is not so easy, right? So because you cannot script it, you cannot plug it into other software so easily. So I think each software can be good for one purpose, and Lead DBS may be too complicated for clinical use. So these are just options that there are. This is an older slide with a similar visualization of the open source market. I think these two are the only ones that are really available in open source and free of cost. DBS Proc, as I told you, builds on AFNI. So if you're familiar with AFNI, this could be a good choice. If you're familiar with SPM instead or MATLAB, maybe Lead DBS is more natural for you to use. Okay. So why did we even start this? A lot of people have asked me, why did we program such a tool if there are these commercial products on their way, so why did you do this? A lot of people have asked me, and one thing that I really like about the open source market is that you can use all these tools like SPM and ANTS and Brains and so on that have been developed over 20 years, and we can just use them. So we can basically take advantage of a lot of research in the open source market where we can use these tools and integrate them into our pipelines. Really briefly, we started Lead DBS in June 2012 already, so 6 years ago, really long time. It's of course based in MATLAB. It works with MRI and CT pipelines and so on. It can do some fiber tracking and so on. And you'll see all that. This is how it looks like. Most of you have seen it. That's the main GUI. But there are also other tools inside of it. It's a bit older slide. Oh, sorry. Where we have the lead connectome and group analyzers and so on. And we're really happy. We recently had 7,000 downloads, so we're really happy that so many people over the world use it now, and we get so much feedback, and it's really becoming an open source tool. We have downloads from really large institutions and big name institutions, but we also have downloads from very far away places for us, like Tsinghua, or For us Germans, or also Shanghai is here, we're really happy that people use this, and then also from German universities. And yeah, so we had the first Lead DBS workshop 2016 in Berlin. That was the first experience. Also 30 participants, and I think we could learn from that one a bit, and hopefully can do a bit better job now. So then we also had a Connectomics deep brain simulation meeting 2017, and as you know, we're now really happy to be here today in Shanghai for the second Lead DBS workshop. What's also really nice is that a lot of people from other institutions have started to develop on Lead DBS, so it's not only made in Berlin anymore, but we now have other people like Todd Harrington really started early from Harvard Medical School, but also the Pittsburgh group is now really digging in and devoting a lot of energy in improving Lead DBS. And you will meet Frank Hertel tomorrow, who with Andreas Husch developed a PACER toolbox, and so on. Then also Theo Dembeck from Cologne started to integrate a lot of tools. So I show this slide here also because we are also inviting people that want to contribute to Lead DBS. It's really open to contribute. So if you think some things could be better or made differently, approach us and bring yourself in. And really important also, we have, I think, a website where we try to have some good resources. So it's worth it to explore this. We have a newsletter which I think is pretty crucial, because if we would find a bug or an error in the pipeline, we want to be able to reach the users. So we don't really send out a lot of emails, but if you use it a lot, maybe register here, so if there's a problem we can reach you. Then the other thing under help support, then there's a knowledge-based thing, and in here we have these walkthrough videos, which it's only one video currently actually, but that can be really helpful as well at home. And then under help support, we also have 3 options where you can ask for help. One is the Slack user channel, and there's a link to invite yourself in here. And then there's neurostars.org, which hasn't been used that much, but it's a great support website where you can post questions, and then we also on the website we have a Lead DBS forum. But I particularly wanted to draw attention to the user channel, Slack user channel, because I also, so in this Slack thing, I also made one group, one channel which is called Workshop 2018. If you want, you can use this during the course and afterwards to connect with each other and ask questions, and just communicate. And I wanted to quickly show you this. So maybe raise your hands who knows Slack, who has used Slack before? Not so many. Okay, so it's a bit like WeChat, I would say, just for more professional use, I would say. And I checked, it's not blocked in China, so you could use it, I think. And there's this. This is the lead user channel. We also have a developers channel here, and then there are people asking questions. So Svenja's from Madrid. She had some problem with registration, and then we could solve the issue. That was just the newest one, but it doesn't really work for me currently. So here it is. So I created this channel. So if you want to enter the Slack channel to get support, you can also enter this Workshop 2018 channel where you can then chat with us. And if you have questions maybe to install Slack or whatever, maybe you ask us in the breaks or ask Lingfei if you want to do this, just an option. Okay. So, then there's also one other very important thing that we built Lead DBS, and currently still in Berlin a lot. Actually, it's Ningfe and me. Mostly, I would say, 80% or even 90% is what we two do. And it's become a big software with a lot of features, and there are always some problems because we are such a small team, right? So there will be errors when you use it, and you shouldn't be surprised. And we try to fix errors soon, but especially in the features that are more advanced, there might be problems. Even here in the workshop, there might be things we cannot demonstrate because they're broken. It's unfortunately the problem of such a small team. And this is just like an old roadmap I once made. This is Lead DBS, and then we have Lead Connectome, we have the core functions, and so on. Then we have the group functionality. And for us too, it's really hard to get a good overview and test everything all the time, because we're also scientists, we also need to publish, and so bear with us if there are problems. The good thing is it's free software, but the bad thing is we are a small team, and there will be problems. So always problems, and then we also think everything can always be improved, so we constantly try to make things better, and even things that work really well, we always try to think about how can we make this better. And so we think the development will never be done, we will never be finished with Lead DBS, but we will probably try to improve it all the time. And now you are now taking this course, and hopefully you will become an expert in Lead DBS. And maybe if you're good with computers, you can even come from a user level and become a developer at some point yourself and contribute. So we always invite you to do that. If you find bugs in Lead DBS, first thing is please don't be surprised. It happens. We are sorry. Second thing is, if you have the time, please report it. Then we can, so either on Slack or on GitHub or wherever, if you find the time. And even better, if you can also fix it. Okay. Right, so some new features of Lead DBS 2.0. We have now segmented leads, where we can also model steered stimulation fields. And we have quite a few atlases inside Lead DBS that people contributed. So that's also a way, if you have a great brain atlas, contribute it. And then also what's important to know that there are two types of atlases in Lead DBS, right? So if you, about anatomy, if you're interested in anatomy, we have basically parcellations which are more for connectomics, and they are more the whole brain definition, right? So we have, for example, everybody knows the AAL, the automated anatomical labeling. It's a whole brain atlas that divides the brain into multiple parcels. And we can use these for parcellations. And then there are the subcortical atlases, and they are more for the where's the electrode, and they are in here. And we have on the website, we'll quickly show you. We have we should have overviews about under knowledge base, atlases, resources, there are the two. So we have the subcortical atlases and we have the parcellations. And if you click on subcortical atlases, you will get information about each atlas that is installed in Lead DBS, and like which publication to cite if you use it, but also where to get more information about it. And the internet is not so fast here, but yeah, maybe you can check it out on your site. And the cortical atlas parcellations, they are more for whole brain parcellations. Maybe quickly to dive in already into, so this is my Lead DBS installation here. Can everybody see that? And inside there's a folder called templates. And in that templates folder, we have space definitions and space. And under space, usually there should only be one folder, which is this one, the asym. And here you have the labeling folder, which is the parcellations. Right? So these are the whole brain parcellations. And then there's an atlases folder, which is for the subcortical atlases. And so this is where these files are stored, but we'll also get to that later. Here you can see the file now, so you have a description about each atlas that is inside Lead DBS and like which paper to cite and so on. And yeah, you can get good information there. There's also the possibility to use to have like fiber atlases, right? So fiber tracks that are in the normative brain that are more definitions of fiber tracts. So there are two types of atlases actually. These are also fiber tracts for like more depression tracts. And then you can use, for example, Lead DBS to see, you put on how much stimulation and you can see whether it maybe should get a capsule effect of this is the corticospinal tract, and if you put a lot of stimulation on it, it touches it, and then you also get maybe side effects. I just already said it that 2.0, so the new version of Lead DBS, sorry, it's not a week ago, it's been even half a year ago now, it's the old slide, I'm sorry about that. But still, the new features I wanted to briefly highlight. One is this new atlas that we made ourselves. It's called the Distal Atlas. It was together in cooperation with the Montreal Neurological Institute, especially Marla Chakravarti, who has a really great histological atlas, and we used a lot of time to register it into our space, into the MNI space, the newest version space that Lead DBS uses. And so we used histology to define some areas, but we also used tractography, so DTI, to parcellate the subthalamic nucleus, for example. And that's another slide about this. So this is the final parcellation of the SDN. It's based on connectivity to sensory motor, associative, and limbic parts. As you can see, it was more a gradient, and then we thresholded it to get a three-party parcellation. We also did that for the GPI. And one nice thing about the Distal Atlas is that, so this is the space in which we work. So if you're new to it, we will get to it later. So this is the MNI space, or standard brain stereotactic space defined by the MNI in 2009. And you can see the subthalamic nucleus here. It's this dark shade. And
sorry, is that you? I think maybe only this part is pronounced as it's pronounced.
I actually kind of agree with that.
Sorry?
I agree with you.
Yeah, you're probably right. So
because in this slide we saw.
Yeah, the back part of it is probably Niagara.
Yeah, this part is probably Niagara. You're right. Yeah. So true. I would have to see more slides to be sure. But
yeah,
if you're sure, then okay. But one thing is that if you now take this part and overlay atlases of the SDN that you can find on the internet, for example, this is an Amsterdam atlas, and they are all defined for MNI space, but the definition of what the MNI space is also loose, and then you will see that they don't match this dark part that much, and yeah, some so this one is really off, for example, and the Tylirac atlas is also off, and if you overlay them all, they're pretty scattered, and our part was to find one SDN that really matches this template quite well. And I'm pretty sure this is correct, so this is not the Niagara, because we really had a lot of really great imaging to look at it, and took a lot of time. And what also is nice about it is that it comes in different nomenclatures, so there are three 3 different nomenclatures for the thalamic parcellations. So you can switch between Hustler and Walker and Hira and Jones nomenclature, Glore nomenclature, to look at which parcels are called how in all of these parcellations. So also just to look at anatomy, this might be interesting. The other thing is that we, as I said before, we have this segmented lead VTA model, so segmented leads, but also the possibility to create a volume of tissue activated, so the stimulation volume around the DBS for segmented leads. Now, and what you'll hear about tomorrow is Pacer, which is also now integrated. It's a fully automated electrode reconstruction algorithm, and then that might be interesting for you, someone there, the MER microelectrode recording mapping tool, where you can place microelectrode recording findings into anatomical space as well.
How do you do that?
Sorry?
How do you actually map the trajectories?
So
how do you enter that information?
Based on the macroelectrode.
But how? Based on the microelectrode trajectory from the frame, or based on what information do you use to actually, because you don't have it in. So how do you reconstruct the trajectory?
So we first reconstruct the macroelectrode, and we'll cover this later as well, right? But you reconstruct, you find out where's the macroelectrode.
How? That's my question. How?
This is what this is about.
Okay, alright.
So
we'll get
based on post-operative imaging, CT or MRI.
Not intra-optic
CT. You don't have it anymore, right?
Sorry?
You don't have it anymore. The MER electrode, by the time you get the post-op CT, you don't have it there.
Yeah, but you will get the macroelectrode. So it's the DBS electrode.
But the DBS is fine, but that was my question.
Okay.
How do you get these?
It's not.
This is just relative to the DBS electrode. Right? So
you have to use the frame information to get it?
No, you assume that the central is where your DBS electrode lands.
Oh, I see. Okay.
Yeah, it's indirect.
Right.
Yeah. There is actually, so I didn't develop this, this is from Ottawa, but there is the option to put in all the next frame information. I haven't done it myself, so I cannot show you.
That was like
But if you have the next frame system, then you can enter everything precisely and it will. But I'm the wrong one to teach you that, unfortunately. Okay, another thing is the human motor thalamus atlas. That's also histological data from Estonia, from Christine Igor Ilinski, and I think they are famous anatomists for anyone who's interested in the thalamus. And they have a nice staining technique which they use to stain the thalamus, and it represents the afferent connectivity systems of the thalamus. So we also, what I did was only to also register this to MNI space. So that's another atlas that we added here. So in a nutshell, we have new VTA model, we have Pacer to automatically reconstruct it. We have this distal atlas, we have microelectrode mappings, and there was also a lot of other things in Lead DBS 2.0. Okay, so quickly, we have time. Okay, so applications. What did we do to use this scientifically? These are old examples actually. I have some more newer examples later in different talks. But just to show you what you can use Lead DBS for. So one option, one study we did once is to find out whether the subthalamic nucleus or the caudal soma inserta was the better target in Parkinson's disease. Right? You may know the study in brain by Plaha from 2006, where they found that the caudal soma inserta, so this part of the brain, is better in Parkinson's disease. And in Berlin, we then did a randomized blind study to test it, and we actually, unfortunately, we found the opposite. So we thought SDN is better, but the target was the UPS motor score after 12 months of medication. And this was reconstruction of the SDN cohort, and we had a few patients that were then also implanted in the caudal soma inserta. So first thing, this was really early work when Lead DBS was still new, was that for me it was nice that we could even show this, right? That we could show the yellow ones are posterior. Now I'm more confident, but this was great at the time. And this is a view from below, and we also see the Sona inserter group and the SDN group, which shows two cohorts. And clinically, we didn't find it, so we had much more levodopa reduction in the, much less in the Sona inserter, much more in the SDN, and also the UPDRS improvement was much better in the in the SDN cohort. But then we also had a few examples. For example, one patient of this Sona inserter cohort showed really good clinical improvement, and we wanted to know where is her electrode, and it was actually pretty much in the dorsal part of the subthalamic nucleus. And if you overlay this together also with the rest of the cohort, so this is the SDN cohort, and this one that was really good was the closest to this cohort, right? So it's a border patient that luckily got it into the SDN. Then there was also one SDN patient that showed no improvement, or not really good improvement, and unfortunately his electrodes were not placed inside the subthalamic nucleus and were not placed well. Again, visualizing it with the Sona inserter group, at least this one was more or less inside the Sona inserter group, but it was just not well placed. Right, so this was first evidence that you can use this to make inferences about single patients. And then this is also a really old image, but you can see that we can also stimulate the volume of tissue activated, or VTA or VAT. And what we did here in the also early study is to localize all the electrodes, then to model the VTA, and then we calculated the intersection between the VTA and the STN in blue. So this volume of how much STN is stimulated in each patient, then we correlated it with clinical improvement. And this was never really published, unfortunately, but we had really nice, at the time, correlations between how much STN, so this is hemibody, this is full score improvement, so how much STN do you stimulate and how much improvement get. So these are the types of studies one can think about. This is, of course, very basic.
Yes, you have noticed that, just out of curiosity, did you have any split between tremor improvement and rigidity very?
Not here, no. Now we did in a much larger study, and so the sweet spots are different at least. Tremor is much more dorsal. This was really early work, and at the time I didn't know the literature too well. It was hard to publish, and we then stopped. But yeah, it's still, I think it's still the most basic study, right, to do. That's why I still showed it somehow.
I've done a similar study.
Oh, good. Yeah, I think there are maybe 30 studies like this in the literature, so it's probably not new enough anymore. But what you can also do is to basically color the VTAs with the improvement, right? So weight. So put in, say this one has a really good improvement, or this one has a good improvement, this is a bad improvement. So to color them, and then you put them all into the same space, and then you can create these heat maps of an optimal sweet spot. And this has been done multiple times, so don't waste your time on it. But what you could do is maybe to take a different score, right? Not UPDRS, but some improvement, or some task metric, or some local field potential recording, whatever. So you can be really creative and put things together and map symptoms that way. And here in this old study, we also just showed that there's better improvement in the STN. Well, that's pretty basic. Similar thing in Tremor, also not published, but we had just the active contacts here. We didn't model the VTAs, but we just put basically the tremor improvement scores onto that contact, and then you can interpolate. We'll show you that in lead group, And you basically just have a finer resolution, and then there was this sweet spot here in the middle, which if you threshold it, then gives you this region. And that region actually is directly below the VIM, so where people also think the rest tremor spot is, or at least that's how far as I understood it. So basically directly below at the inflow where the cerebellar fibers go inside the VIM. In this study, small study, not published, we had the highest improvement here. Okay, this was the first part. Just as an introduction, what this is about, what we plan to do, and some basic examples what you can do with these. Any questions so far? Yes.
You have mentioned the two kind of animals, the subcortical animals and the whole brain. I want to mention the two kind of animals. One is the stereotactic coordinated based animals, such as the direct animals. I have read the manual of the Lead DBS by Boston Scientific. As you know, there's no product of Boston Scientific need and no product, but I have read the manual. The Lead DBS software choose the more animals, more animals.
Yes.
First, the software defines HPC and reveal the stereotactic coordinate. So the question is, what's the difference between the two animals? You choose the MRI,
yes,
and the another software choose the
ACPC. Yes. So we'll actually cover this in one talk in detail, but in brief, I would say that ACPC is the surgical standard that people use, but it doesn't account for patient-specific changes in the brain volume. Right? If you have a large brain, maybe 11 millimeters lateral can be medial to the STM, but in a small brain it can be lateral to the STM. You understand? So if you say the optimal spot is 11 millimeters, it can sometimes be lateral, sometimes be medial to the STM, which is a big problem. Right? It's useless in my view. And the MNI brain is similar, but tries to non-linearly register the STMs and all these structures to each other. So my short answer is don't use ACPC. But I'm maybe alone with that. But so he's great. All right. If there are no further questions, we'll just move on to the next talk, which will be more interactive and more practical. This is about linear co-registrations, and so when I planned this course, I thought this is the first theoretical talk, and it's going to be a bit the only one in the whole course which will be a bit complicated. And I did so to start this because maybe you're now still fresh, you're still not tired, and you can do a bit of also mathematics. Not mathematics really, it's not going to be very complicated, but all the rest of the other talks will be easier. So if this will be maybe a bit complicated for you, don't worry, right? So the rest will be easier. It's the only one where I try to make things a bit more formally, and it's not, for most people it won't be really complicated. So registering two images is very, very important. It's the most fundamental thing in this whole imaging world. So that's why it's crucial. And so registering two images is basically you have to maybe the same brain or two different brains, and you want to overlay them, right? We have two pictures of my hand, and we want to find a way to mathematically put them on top of each other. That's registration or co-registration. And in the SPM world, so because SPM from London is a very influential software, they say co-registration for linear co-registration, and then there's normalization, which is also a co-registration but between two different brains. So these are the nomenclature, so the words we also use. If we say co-registration, it's the linear version. Normalization is the nonlinear. And I'll get to what that is in a second. So co-registering, this talk will be about the linear part, which means that I have to find a rule that I apply to my hand, which is the same for every part of the hand. Nonlinear could mean that I could take maybe one finger down, and that's nonlinear, right? So if I want to register this hand to this hand, I would have to squeeze this finger down. So that's nonlinear. Linear will be same rule to every pixel. And we usually use the linear one, the co-registration, for the same brain, right? If we have two pictures of your brain, we will use usually linear registration. If we have two brains, two different ones, then we would use nonlinear because we have to account for the small features. And usually we don't register two different brains, but we register one brain to a template of the MNI space, right? So the next talk after this will be about, no, will not, no, the one after that will be about normalization, so about the nonlinear way. Now only linear, so we stay within the same patient. We have a preoperative scan, we have postoperative scans. Usually we have postoperative either an MRI or a CT, and preoperative we often have a T1. We also often have a T2 because we want to see the SDN. Usually we don't have a PD, but some people do. And there could be other sequences, of course, right, that we have preoperatively. And postoperatively, either or sometimes you have both of them and you have to choose. And this process is really just about how to fuse this MRI to that, right? And I would say, some people would say this is really simple, there's usually a button for it and you click it, then it's done. And I mean, often it's right, sometimes it's not. That's why I make this a bit more complicated. Because sometimes, I would say even you need a manual way of doing it. Because if you have poor imaging quality or you have some different reorientation problems, it may be important to be able to also fix these problems. Just briefly what I just said, once you have co-registered or fused the pre- and post-operative images, so here we have a CT with the electrodes and the MRI from pre-operative, then in Lead DBS we normalize or we non-linearly register to the MRI space, to a template, right? And then we have really good definition of one normative brain, like a normal, healthy brain in MRI space. So we want to move this information to that or the other way around. And the reason we do that is that we have atlases in here, very good definitions of what each structure is, and we want to use that information in our patient as well. Okay, so then, as I said, this is a bit more technical, but there are two ways that are usually used to define a point inside the brain of a patient. One is the world coordinate system, and one is the image coordinate system. So world coordinate system is in millimeters, and it usually has some point which is 0, and that's usually the AC, the anterior commissure. And then you have a system that says, 2 millimeters left and 3 millimeters up, and so on. In the image, instead you have a big matrix, and there's a 0 point, and then there are the data values of the image. So this is voxel coordinates, and this is world coordinates. And I wanted to quickly show you the difference. This is a very, very small demonstration. It just opens an image, and we should be able. So this is an MNI space image, and if we enter 0, 0, 0 in millimeter in world space, we'll get this coordinate here, which is close to the AC, to the anterior commissure. But we also see a different coordinate system, which is the voxel coordinate system down here, which is how the image really is stored. So the entry number 46, 64, and 37 is at the 0 millimeter space. this is not so important, right? It's just a way of how the images are stored and how the registration into a world space is stored. And this is done by a matrix, so this transformation that we'll talk about in the next slides. Okay. So this is this matrix that is stored in the inside of an image, and if you multiply the one coordinate with this matrix, then you get the other coordinate. Right? So this such a matrix. You don't have to maybe understand all the details, but such a matrix can be used to translate between one set of coordinates to the other. And if we make a co-registration between two images, then we can always define this co-registration as such one matrix, if it's linear. Okay? And for people that are interested, there's a really great website which is called matrixmultiplication.xyz, and it shows you how these multiplications are done. So here you can see visually what happens mathematically if we multiply these two matrices, and then you get the result. So in our case, we always calculate a coordinate with a 4 times 4 matrix, and then we get a new coordinate. Okay, but also not so important. Maybe what is a bit more important is to know roughly, so this is such a fine transformation matrix, roughly to know where the important entries are. So these entries, they make a translation, right? So if we change this one, we will move the image in the x direction, and you'll see that in a minute interactively. If we change this one, it's in the y direction, and if we change this one, it's in the z direction. So of this matrix, these three are important, and these three are also important. I think you'll see that in a second. No, that's rotation. It's more complicated. But here, the zoom, so scaling, these three entries make images bigger. Right? If we have a larger value than 1 here, then it will be stretched in x direction, here in y, and here in z. And then there are shares, which is, sharing the image like this, that are also stored. So basically, what these slides tell you is that with such a matrix, you can put all these operations to an image. And this is usually how they are then combined, so not so important. But I have one other demonstration script. That is here. So all this does is that it loads an image of a brain, and it will then apply this matrix to the points here, to the coordinates, and then you will get the transformed version. And now currently we just have an identity matrix, so nothing special, so 1, 1, 1, and it will just create a copy of this brain. But we can now do things with it, so we can say maybe we want to add 1.5 here. Does anyone remember what that would do? Sorry? In the y, yes. And so exactly, so that will be larger now, and so you can see that this is our brain, and the other brain is stretched in the y direction. Right? 1.5 is already pretty much, but if we make it maybe smaller, then we'll get now it's smaller in y direction. Right now it's, you can see it's been squeezed together. If we instead take these, maybe 0.4. No, that probably we need something bigger here. Then we would move it in x direction, right? Now it should be slightly moved. You can see that there's more distance here than here, right? So all this script does is really to, at this point, multiply the coordinates with this matrix, right? So this is a way of demonstrating this. Okay, and what I wanted to do now is maybe to make this more graspable or easy to understand is to open an image of a brain in Slicer. Does everybody have Slicer installed? The software, so you can, if you want, you can also start it now. And we can just internet. Do you have this internet?
Yeah.
Yeah.
Yeah, I think it's because of the Chinese firewall, so you cannot actually access the Google.
No, it's not Google.
That's
Any questions so far at this point? Problems? So if you haven't used Slicer before, it's a really great software. It's also free and open source, as you can see, and it's developed at the Brigham and Women's Hospital in Boston, so at Harvard Medical School, and a great team of nice people. It's developed in Python, and it's also a fully functional. Change this one, it's in the Y direction, and if we change this one, it's in the Z direction. So of this matrix, these three are important, and these three are also important. I think you'll see that in a second. No, that's rotation. It's more complicated. But here, the zoom, so it's scaling. These three entries make images bigger. Right? If we have a larger value than 1 here, then it will be stretched in X direction, here in Y, and here in Z. And then there are shares, which is, sharing the image like this, that are also stored. So basically, what these slides tell you is that with such a matrix, you can put all these operations to an image. And this is usually how they are then combined, so not so important. But I have one other demonstration script. That is here. So all this does is that it loads an image of a brain, and it will then apply this matrix to the points here, to the coordinates, and then you will get the transformed version. And now currently we just have an identity matrix, so nothing special, so 1, 1, 1, and it will just create a copy of this brain. But we can now do things with it, so we can say maybe we want to add 1.5 here. Does anyone remember what that would do? Sorry?
Larger in the X.
In the Y, yes. So exactly, so that will be larger now, and so you can see that this is our brain, and the other brain is stretched in the Y direction. Right? 1.5 is already pretty much, but if we make it maybe smaller, then we'll get now it's smaller in Y direction. Right now it's, you can see it's been squeezed together. If we instead take these, maybe 0.4, no, that probably we need something bigger here, then we would move it in X direction, right? Now it should be slightly moved. You can see that there's more distance here than here, right? So all this script does is really to at this point multiply the coordinates with this matrix. Right? So this is a way of demonstrating this. Okay, and what I wanted to do now is maybe to make this more graspable or easy to understand is to open an image of a brain in Slicer. Does everybody have Slicer installed? The software, so you can, if you want, you can also start it now, and we can just Internet. Do you have this internet?
Yeah. Yeah, I think it's because of the Chinese firewall, so you cannot actually access the Google.
No, but it's not good.
That's
What are you interested
Any questions so far at this point? Problems? So if you haven't used Slicer before, it's a really great software. It's also free and open source, as you can see, and it's developed at the Brigham and Women's Hospital in Boston, so at Harvard Medical School, and a great team of nice people. It's developed in Python, and it's also a fully functional neuroimaging platform, so you can do a lot of things with it. Also diffusion tractography and so on. So if you want to spend some time learning software, Slicer is also really cool software to use. And we'll just explore a very basic function of it. And what we will do is to so you have the files, right? These are the patient files that we gave you, but you can use any other file as well. And what I'll do is I'll just drag the T1, so I'll pull the T1 and drag it into Slicer to open it, right? So maybe again, show you, take the T1 or take any image actually and put it into Slicer, and then you can open it.
If you have problems, you can raise your hand and I can come and help you.
And what I now simply wanted to show you is that we can, up here in this button, there's a transform option. So this with the two images where you can already see this is about creating transforms, and then in here we can select the linear transform and we can say create a new transform as. Right, so maybe try to find that button, everybody. And if you have that, you can just enter your name, a name of it, maybe my transform. Yeah. So again, it's this button up here for transforms, and then here we said create new transform as, and we gave it a new name. And all we have to do now is to apply it to this image, right? That's the T1 that I opened. So if I click on that and put the, click on the right arrow here, then now this transform, my transform, will be applied live to the T1, right? So your screen should look like this. It's not so important if you cannot follow this now, because this will be over in a few minutes already. So this is just about showing you how these matrices work in practice. And you can also see up here now in the transform matrix, this is basically what we have just seen, right? So it's the same transform matrix as we've seen in the software. We have seen that these are the the zooms, and these are the translations. So if we now would put something like 4 here, or 5. Now if I press enter, the image will move to the left, right, in this case. So we can use this. You can also enter, so move this slider here, which will do the same thing, and this will just move the image in space. Right? So this is a way of exploring these matrices. If we put maybe something like 1.5 here, then we'll have a larger brain in X there. So it was made bigger now. And then there are the other things like rotation also, which would make pretty complex. You can see these will change with the sinus and cosinus functions of the degrees, and but still it's all stored in this matrix. Okay. So all I wanted to show you here is that these affine matrices are a good way of storing information of how to register two images. And as I said before, this is the probably most theoretical talk of the whole course. So if you're a bit lost now, don't worry, right? This is more, it might be important later, and we'll have a second part where Friederike will show you to use slicer to actually register two images manually. And you will probably need that at some point if you have maybe a poor resolution CT or some problematic image, then it's really good to be able to register two images manually outside of Lead DBS. And you've now already learned that these matrices, how they roughly work and how they store. Shall I give you 5 more minutes to play around with this? Or? Yeah.